Today we're going to start talking about electromagnetic induction. Oftentimes in physics, we start out with a contrived example. Today's contrived example is an imaginary, floating, straight conductor moving at constant velocity through a uniform magnetic field. All right? And what we will see is we will see an EMF, or a potential difference, okay? It's something we also call voltage, all right? It's going to build up between both ends of our free-floating conductor. So what happens is that electrons, all right, that are in the moving conductor will experience a downward magnetic force if we follow the diagram that we have here. And what that ends up doing is leaving a net positive charge at the upper end. Now, I don't know if you remember from when we studied magnetism, all right, that a moving charge gives rise to a magnetic field, and that a charge that moves in a magnetic field will experience a force. Both of these things are things that we studied. Now, when we deal with positive charge, we have the right-hand rule. All right, and with the right-hand rule, what we typically say is that we have our fingers pointing in the direction of the magnetic field, right? We have our thumb, z direction coming out of the board here, pointing in the direction of the velocity of the charge. That's the velocity of the positive charge, all right? And our palm points in the direction of the force acting on that charge. Well, if we have negative charge, we can just use our left hands and keep all of the parts the same, all right? So let me just label this here. The magnetic field, again, is our fingers. And I like to use this right-hand rule and left-hand rule because each of these items intuitively matches, in my opinion. In other words, my fingers look like magnetic field lines if I hold them a certain way. My thumb, if I hold it out at a right angle, is like the velocity vector of the charge or the direction of the current. And my palm is a forceful part of my hand. That's where the force is coming out of. That's my ridiculous way of remembering. You can always make up your own. I believe the FBI got us another way that some people do it. Yeah, there's a bunch of different ways. So choose yours and stick with it is what I would say. So negative charge, all of it holds except you're using your left hand now, okay? So when you use your left hand, all right, if we're going to keep what we had before, what we're going to have to switch is one of these directions. And in this case, let's switch the magnetic field, right, make it go this way. So this will be following our left hand. Magnetic field goes this way, right? What ends up happening is the velocity of the charge is this way, right, in the same direction as before. It's the thumb. We've got this straight up thing happening. The force from our palm, okay? I bring that up because in this conductor here, we're going to be looking at the movement of the electrons, right? And if we use our left-hand rule, we can see the direction that the force is supposed to act. So the electrons are in the conductor, they're moving to the right, so put your left-hand thumb in the direction of the velocity vector, which is to the right, okay? Magnetic field lines go into the board, so point your fingers into the board. Which way is your palm pointing? Hopefully your palm is pointing down, okay? And so what we see here is positive charge builds up at this end. The electrons are going to move down here. We have negative charge building up on that end. All right? So as charge builds up down on this end, what we end up with is a potential difference. So let's start with the derivation. All right? Remember that the magnetic force here is going to be equal to the amount of charge times the speed times the magnetic field strength. All right? Really, that's a cross product between the velocity and the magnetic field. But you know, we're not going to be dealing with that right now. When you get to that later in your scientific careers, you at least maybe have heard it before here. Okay, so we use the left-hand rule for electrons. All right, to show the direction of the force. We did that. Direction of force on the electrons. And what this does is that this creates an electrical field, okay? We have this little bit of a difference here between both ends. What we notice is that after a while, that magnetic force pushing those electrons is going to be balanced out by the force of attraction between the oppositely charged ends. Okay? When that happens, move up here. We're going to say Q times B is equal to Q times field strength. All right, our charge is going to cancel out here. Okay, this is the force acting on a single charge. Both charges are the same. And what we end up with is the electric field strength should be equal to, when everything's balanced out, the speed of the conductor through the uniform magnetic field, the product of those two. All right. The potential difference that builds up will be built up over the length of the conductor. So whatever the electric field strength is, all right, over the length of the conductor, let me go to the slide here. All right, will tell us what the potential difference is between both ends. We have this equation from topic 6, or topic 5, okay? And that is the potential difference is equal to electric field strength times the distance between 2 points in that electric field. Well, I'm going to substitute the length of the conductor for delta D. That's the length that we're going to consider between both ends of the conductor. We want that potential difference. So we see here that's equal to electric field strength times L. All right. If we solve for E, which is equal to delta V divided by L, we're going to substitute this equation into the previous one we had, which was this. Right? We have delta V all over L is equal to V times B. What we see is that the delta V, the potential difference set up across that wire, is going to be equal to the speed with which that wire is moving through the magnetic field times magnetic field strength times the length of the wire. We can rewrite this as the EMF. All right? And I'm just going to reorder these variables. There you go. So you see here in the next slide, if we actually put that floating wire into a circuit and complete the circuit, the induced EMF between both ends of that wire is going to produce a current. Okay? So that's pretty much equivalent to having a battery in the circuit, right? Anytime you have an EMF source. The direction of the current, okay, is going to be based on the direction of the movement of the charge. If we go back to this previous one here, we see that the electrons are moving down. Well, since this wire, okay, is moving in the same direction as it is in this example right here, the electrons that are moving down, remember, current, we talk about current as the flow of positive charge. If you don't remember that from last year, whenever we discuss current in a circuit, we're always thinking of it as the flow of positive charge. That is conventional current. That goes back to Ben Franklin and arbitrary assignments of what was considered to be positive or negative charge. Okay? As long as you stay consistent with it, you'll be fine. So even though the electrons are moving, if you look at this circuit, in a clockwise fashion, all right, the positive charge is moving in a counterclockwise fashion. So again, that's from the right-hand rule of the forces on positive charge in the conductor. Before, we were looking at the left-hand rule because we wanted to deal with developing that equation for potential difference. Okay? So the amount of current in the circuit, though, is simply given by the fact that the EMF will be proportional to the current of the circuit times the resistance. All right? So if we solve for the current, we substitute this in. All right, substitute this in for our definition of the EMF generated by a long, skinny conductor in a magnetic field. All right, what we end up with is the current is equal to the magnetic field times the length of the wire times the speed with which it moves divided by the resistance of that wire. An example problem might be determine the magnitude and direction of the current in this rail system. If a rod of length 1.6 meters is moved at a steady speed of 5 meters a second through a 0.80 Tesla magnetic field, the rails have negligible resistance, but R, the resistor that's in the circuit, has a resistance of 96 ohms. Okay, so this is just simply plugging and showing the EMF produced by moving this rail at that speed through that magnetic field. This equation right here. All right. and this is equal to 6.4 volts. The current, therefore, just the EMF divided by the resistance, and this is equal to 0.067 amps, and the direction of this is counterclockwise. Or as the Brits and IB folk like to say, anti-clockwise. Look for that on the IB test. Alright, so we got this idea of electromagnetic induction, the fact that we move a conductor through a magnetic field and an EMF will be induced. That is the induction part. Okay? That is the connection between electricity and magnetism that's going to allow us, to generate electricity. All right? That's a beautiful thing. So we need to create some definitions for magnetic fields and all of that business before we move on, and we'll do that in the next video.